some hardware instrumentation, the rack behind it. We have a foam column and then some kind of target up on top. So this kind of configuration would be for measuring radar cross section. All right, this is the type of facility that's used, and I've done a lot of work in ranges like this. My team here, Larry Tyketch, Chris, Chester, Mayor, Angelo, they've all supported this work in some fashion or another over the last 2.5 years. The outline for my talk, I want to first discuss radar performance specifications of this commercial off-the-shelf radar that we've evaluated. Then I want to discuss how the free space propagation loss influences these performance specifications and what that means. Then do a couple of slides on transmitting antennas related to the Europa Clipper science mission. Some work also going on in ETR. Then discuss some measurements we conducted in 2018, radar measurements and antenna measurements on drones and using this radar. And then finally talk about some Doppler rail measurements, which are used for tracking. If you have a tracking radar, you need to have something moving. And so we developed a technique using a Doppler rail to make that motion to assess the trackability from the radar. And then finally, discuss some of the flight data assessments, flight tests we conducted, and then conclusions and recommendations. So here's the radar specifications. When they say object RCS, what they really mean is dynamic range. So what they're telling us is their radar has a dynamic range of -50 to +100 dBSM. I look at that specification, I kind of snicker, because the best laboratory instrumentation I've ever used, if they claim 110 dB dynamic range, and now we're talking linear dynamic range, 110 is about the best I've ever seen. So for this spec to be 150, I kind of question that. Then the other statement they have here, for a 0 dBSM target, first detection is at 2,500 meters range to have a 90% probability at 10 to the -6th false alarm rate. That's kind of how these things are spec'd. You have a probability detection and then the false alarm rate based on that. So what the company here is saying, and I had to negotiate this information so I could publish it. This is not what's in their manual when you buy the instrument, but this is what they've allowed me to say. In terms of the range resolution and velocity resolution, this radar did not have that, at least right now, does not have that variability where you can change the waveform and change the resultant range resolution and velocity. When we've collected data, we've received a range resolution of 3.25 meters, and the velocity resolution is 0.91. What that means is you cannot define the data any finer than that. Okay, you can only get within 0.91 meters resolution. All right. The other information here, search and track. What this is all about, because the radar is a surveillance radar, it needs to cover the entire scanning range. In this case, this radar operates over a field of view plus or minus 60 degrees in azimuth and plus or minus 40 degrees in elevation. So what they're saying is within a second, I can scan the entire volume of airspace and identify, where a track is. In order to do that, and it's all about timing, they can only maintain 20 simultaneous tracks and cover that field of view. So to me, that's a little concerning. We want to be able to distinguish a track that's important to us, maintain it, keep looking at it with the radar. But things like ground clutter or birds or things like that are not a potential conflict with my vehicle, then I want to disregard that so that I can, maintain this 20 track limit. So that's some ongoing work. The other thing here I talk about, the operational center frequency. This particular radar through FCC spectrum allocation operates over a 45 megahertz bandwidth. They actually have 3 different bands they can choose from within this 200 megahertz sector. Anyway, let me keep going. All right, so the plot here, I show two-way path loss. So the loss number in dB is the y-axis. The x-axis is the range. So earlier I said that a 0 dBSM target can be measured at 2,500 meters, first detection, and that would be at a 90% probability, 10 to the -6th false alarm rate. Since we understand the radar equation and path loss, we can correlate this, map it to, if you will, for different size targets. So if you had a target that was -10 dBSM, then it would be at 1,250 meters, where you would have the same power level, so the same specification. Or if it were a -20 dBSM target, we would be at 750 meters. -30 target would be at 430 meters. Now, typically, the way things are going, a well clear distance from your aircraft is maintained. I think 2,000 feet, which is around 600 meters. That's kind of a rule of thumb, I think, of what well clear are. And what that means is your aircraft cannot get any closer than 600 meters, or you violated this well clear distance, and you're potentially putting yourself at risk for a collision. So with all that said, if you were to look at the target not at bore sight, but at an extreme viewing angle, because these antennas do have a degradation in gain from 0 degrees bore sight versus, say, plus 60 degrees azimuth, you can have a couple of dB gain difference in that antenna pattern, all right? And that would, again, correlate directly to this plot. If we lose 4 dB of signal, it would be just like losing 4 dB signal on the radar cross section. So it's even worse. So a -20 target would be seen first detection at 650 meters and not 750 if you were looking at it at an extreme angle. The other thing this demonstrates to me, if you have targets that are -20, -30 dBSM, we really need to enhance them signatures to have an effective sensor against that. It would be just like driving with your headlights on or having corner reflectors on your sailboat. Both techniques are commonly used to help be safe. If I were a manufacturer or operator of drones, I would want to be seen, and therefore I would want to enhance my signature, which is a pretty straightforward process. It could be done, relatively easily, and a lightweight solution. All right. So this is just to show that if you're at extreme field of view angles, because you have less power in those regions from your antenna gain, then you've essentially shrunken your detectability. So a 20 target at bore sight is 750 meters. If we're looking at it at -60 degrees, then we're at 650. And again, if your well clear volume is 600 meters, that doesn't give you much time to react. So that's kind of a concern. All right, I'm going to jump into different measurements we collected, but before I do that, I want to give you a reference on our coordinate system. So the radar essentially gives a beam pointing angle, which is azimuth and L, and then a range. And you can correlate that into a coordinate system, X, Y, Z, one and the same essentially. If you're making a measurement and you have to rotate that object, it's important that your axis center rotation is the same in both axes. So say you want to rotate azimuth, right? That's one axis. But then if you needed to tilt the target to get an elevation look, it's important you understand where that elevation rotation occurs. Otherwise, you get different data. Just pointing that out. All right, let me keep going. All right, so this is an example of some work that was done in the ETR. What they're wanting to do is have a high gain antenna on satellite Europa Clipper. All right, and it's got to travel from Jupiter's moon Europa to Earth. So you need a pretty tight beam to do that. And by the way, as that transmission is occurring, the satellite is moving, and so is the Earth. So it's, you know, kind of cat chasing a mouse, right? This is an example of that. And I show this because this is what it would be like to be a drone trying to intercept another target in the airspace. But this actual example here is what's actually going to occur. I think it's a 13-day orbit around the Jupiter and Europa, where the signal is transmitted back to Earth when it's able to. Let me play that one more time. Just, you know, so now it's shooting to Earth, reconfiguring, shoot to Earth. Then it's going to focus on Europa, collect some more data, then send that data back to Earth, get new information from Earth on what to change in the next pass around Europa. So kind of cool work. All right. What we were doing in ETR for this work was trying to align the electrical beam with the mechanical references, because your beam could be a little, it doesn't have to be, you know, directly off the center of the dish. You could have a slight tilt or something, and understanding that is important. Some of this work has been, I have yellow blocks here. Some of this are used anyway. Let me just keep going.
George, how often do you calibrate these?
Calibrate what? A measurement like this?
Yes.
So this one's a little different. You see that flat plate? That flat, normally on an antenna measurement, you would use a standard gain calibration, a standard gain horn for calibration. It's well quantified. So you would measure this antenna and then use that, swap it out with a reference cal antenna, and then you can get true reference in dB and gain and all that kind of stuff. Here, what we used was a backscatter measurement as a reference. We know precisely what that flat plate is. So on the other side of this, you know, this is the antenna here, but the other side is actually a very polished flat plate and has a gain. So we use that gain from that to reference the gain of the antenna. You know, you ask me how long or how often. I would think that we did that every day, but I can't guarantee that. You know, the instrumentation, well, typically every day. So let me just leave it at that. Okay. All right, I'm gonna keep going.
Okay, please.
All right. So the next slide here is talking about radar cross section. When radar cross section, it's given in a dBSM value. That's the units, dB per square meter. The information coming from this radar is not a dBSM number. It's essentially a downrange number. dBSM is reserved for the coherent sum of the scatterers within a window. You know, you might have a sphere as a cal object, and that sphere has a referenceable dBSM number, but it really is the integration, the coherent sum of the scatters. For a sphere, it would be your specular response, and then if you're low enough in frequency, you got this creeping wave going around the sphere that's causing a beating pattern, a little bit of oscillation around some average number, and you can make a reference to dBSM. In this case, though, the radar is giving us an incoherent sum. It's sort of a downrange number. So it's really not a true dBSM. So let me just say that. It is a horizontally polarized radar. So that tells me it's going to be the leading edges of your targets that are going to be most influential on giving you that radar scatterer, leading edges, and then speculars, nose on, tail on for a vehicle like this. And we'll see some data here in a second. All right. All right, I'm referencing some work done at the University of Massachusetts Lowell. Very good high-tech radar lab. I worked with them for 5 years when I did some work for the Army. This picture of that T-72 tank, that's a 16th scale model, but very accurately depicted, geometry. And it's sitting on a ground plane. The data on the far right, this 2 gigahertz bandwidth, that would be data collected on that type of vehicle. You can see the turret, you can see the start of the tank. To me, it's very interesting that you get a shadow region behind the tank. Normally, you don't see that kind of stuff, but I've always done my work in free space, essentially, like an airplane flying, not a tank on the ground, except when I worked with the Army. So I didn't see this kind of stuff. So that was neat. But the other image here, if you had 171 megahertz bandwidth versus 2 gig, your resolution is going to be 1 meter. So this is an ISAR image. You can actually establish the size of the vehicle. What the radar is giving us, the one we've been evaluating, is this. It's just a simple downrange cut, and your cell resolution is 3.25 meters. Whoops, I'm going to go back. Point out this formula, delta X C over 2 delta F. What that means is if you want to have finer resolution, then you need more bandwidth. So if you could come up with a radar at 170 megahertz bandwidth, then you can get that 1 meter resolution, which would enable you to better quantify the size. This 3.25, maybe that's good for looking at a Cessna. And by the way, this radar is actually designed to see manned aircraft, not small UASs. Okay, so with that said, is kind of why we get the results we get, I guess. But anyway, my point here, if we could go with a larger bandwidth, we could get finer resolution. And then if you could actually get SAR-like data through some technique, then you can actually get cross-range resolution and get sizing. Okay. All right, oops. Oh, whoops, went too far. Need to move this thing out of my way. Whoops. I'm trying to move this icon. There we go. All right. So with that said, right now what we're looking at, we have a 45 megahertz bandwidth, 1842 frequency steps, and the bandwidth, of course, as we said, correlates to your range resolution, and the number of points will correlate to your total range extent. This radar goes to about 6,000 meters. I'm not sure why that's the design, since a 0 dBSM target can only be characterized, first look at 2,500 meters. So that seems a little excessive. Not that it hurts anything, but just kind of wonder why they did that. What I'm proposing could be done if you had a 200 megahertz bandwidth. You could have a 1 meter range resolution. And if you took 4,500 points, that would give you a 4,500 meter extent, keeping the same the radial velocity resolution, 0.91. That has to do with the number of chirps, the 32 chirps. Again, all this could be changed. Our radar was not allowed. We couldn't facilitate these type of changes, but hopefully the manufacturer is looking at what you could do, because if you could dwell on a target longer, that's the only way, unless you add more gain somehow, it's the only way you're going to get further range distances. Move that 0 dBSM out to, say, 3 kilometers from 2.5. One way of doing that would be to dwell longer. But again, you're fighting the time of scanning this entire field of view, because you got to update that and maintain tracks. So the timing gets pretty complicated quickly. And a couple other things I mentioned on the slide. This radar is susceptible to interference from other like radars operating within 5 kilometers. That's what the manual says. In fact, they tell you to turn it on for 20 minutes and look for telltale signs of interference. So the signs are, no matter which beam angle you're looking at, 0 degrees or say 60 degrees, you have the same tracked returns at that given range for any look angle. So this interference is going to sort of remove your ability to look in that region of space. Radial range distance from your radar. I don't know how much extent that covers, because I've never actually seen it, but it makes me wonder how much better we could do if we actually link these radars together into a multi-static system, so that you can, particularly for these low RCS targets that you can't see until they're 450 meters away, if you had a heads up from another sensor, be it another airborne radar or a ground radar that can pass you information as you're flying in this region, it can only help you, be aware of your environment. So regional connectivity, I think can help it. It wouldn't help our range, detectability in terms of distance, in terms of range, but certainly it would help you be aware of your environment. All right, let me keep going. So this radon work was something I did for a team out there. They were looking to build a 3D printed radome for a radar. Okay, another one of the flight tests, and I was responsible for collecting the data. I show this one. This was Alton Black, which I think is it's in my paper here at 1010. This is a published paper that has this. If you wanted to go back and look, but a very thin coupon that would be radome material like, although it's black instead of this clear. Just flipping that thing over, you get these deep nulls. Now these are good. That means they're not going to interfere with you at all, right? In fact, the radar that I've been testing, we also measured that radome, and it fell right here within the range. So these are acceptable values for a radome material. But I show this because I'm always fascinated with the NASCAR races, where they put this little piece of tape on the front of the car grill, and it helps them handle better, changes downforce. As we get more sophisticated with our tailoring of materials, I could see where 3D printed, dielectrics could really improve the performance of some of our antenna apertures, give you, side lobe reduction, stuff like that. Okay. All right. Now I'm talking about radar cross-section measurements. Here's the radar. We actually rented this for a month to do this. The equipment we had just wasn't adequate to do what we needed to do. We're still trying to stand up this facility, I guess, so we didn't have everything in place. But here's your cowl cylinder, the reflector back there. This is Eddie up on a lift. This is the Tempest aircraft. Okay, here's some radar data, 18 gigahertz, not 24. This radar only went up to 18. Oh, I went past one. Here's the Tempest. So 0 dB SM line, it looks like, only on the cardinal angles do you really exceed that 0 dB SM with this Tempest. So this is azimuth angle on the bottom on the x-axis. Y-axis is dBSM in magnitude. So if I had to guess, I would say, overall, maybe it's a little above -15. The speculars, of course, at the cardinal angles, you get a little higher. Here's a smaller UAS, a Phantom. It's coming in around, say, -17, if I believe my line that I put in here. And then finally, here's a DJI with a radar installed on it. You can see the specular from the radar right here at 0 degrees. But typically it's, -5 or -8 or something for an average there. All right, now I'm turning my attention to antenna measurements. Again, we use the ETR facility. In this case, we put the transmitting radar in the center of the quiet zone. Here it is, and here it is. Looking at the facility itself, centered in the quiet zone, we're transmitting to the reflector back to the antenna. We're using a spectrum analyzer to collect that data, and then we process it into these kind of patterns, these azimuth plots. So this particular plot here is where we were looking at if the motors themselves, we've got an extreme viewing angle. We're trying to look up through that motor. And if there's any difference in these beams, these are at 2-degree increments around that post where that motor is. And we did not see anything. But I also want to point out, this is how the radar actually establishes where a target is in azimuth and elevation. It sends out 2 beams in azimuth, closely spaced, and 2 beams in elevation. And it does an amplitude comparison. It tries to, at a given range location, it wants to equate the amplitude between the measurements. And if it does, then it has a centroid of where that is. Unfortunately, these beam widths, are not finite. So there's room for error. And I think this is the biggest culprit of accuracy, is how well these beam angles, correlate with one another. Here's some other antenna patterns that we collected at the extreme viewing angles. What we were looking at here was how much attenuation loss is there in the gain when you get off bore sight. The manual says 2 dB. I actually measured 2.5 dB. And what that means is you've just reduced your first detectability range that much more. So instead of 4 dB, now we're looking at 5 dB, because the antenna is actually 2-way. You have a transmit and a receive, and they're both identical. So if you lose 2.5 dB, and when you with one antenna, then you've got a total of 5 in both. Also, I wanted to point out the nulls in this pattern. The side lobes are here; they're down relatively pretty well, but that's still a lot of energy. So say you're flying, looking straight out like this one here is, you still have all this energy intercepting the ground, which gives you scatters, right? But also look at these nulls, which is what I want to highlight, where you get these deep nulls, because they're going to be in every pattern. There's going to be a place where you don't have any energy. And this is my concept slide. What I'm proposing we could do, if you could have a second or even a third passive scanning antenna, okay? And it needs to be referenced. You need to have a reference link to the master radar, if you will. But if you could reference another antenna, you wouldn't have to use the main beam to be pointing at it. You could be using one of these nulls. Then you would be looking at a comparison of, is there a signal or is there not a signal? Of course, this is only going to work, say closer to the radar where you have good signal to noise power. It's not going to work, say, at 2,500 meters, but in front of that, it should be a reasonable technique. But rather than doing a comparison of 2 signals to equate the power level at a given range, you would be looking at whether you have power or don't have power. Because if you can point this null and make that scatterer disappear, then you've isolated it better than you could with the main beam. The main beam, this one is elevation 0. Okay, so which is this H plane. So I think this is a 6-degree beam width in the elevation plane, which would be the H plane. That null is like 2 degrees. So you have a much finer resolution in establishing it. And these passive scanning receivers, they're pretty fast. So implementing something like this would be a really good way to enhance the performance of the radar. You can also, I feel, increase your field of view of the radar. The field of view is defined by where is the main beam. And again, in azimuth, it's plus or minus 60. But you have a lot of radiation that is beyond that, beyond 60, right? So I think if you had a second antenna and did this right, you could expand, at least for close in. It's not going to give you that field of view everywhere, but it could give you that field of view closer to your radar. Okay. Jumping along ahead here, the next measurements we did were to try to establish some tracking metrics with this radar. It took us a long time to get our authorization through the government spectrum, the NITA. And so we had to work indoors initially. So this was some work that was also done in the ETR. And we were looking at translating the target repeatedly and changing our variance settings. I wanted to understand how the Kalman filter was influencing the results reported from the tracks. Now, this is pretty noisy data, very ugly, but I think there is a little bit of correlation here in terms of the variance setting and the results. But here it shows the RCS numbers. The next slide. This also, I think, was reported. Yeah, this was reported in a technical report here. Here's some of that data, indoor data. So ideally, the velocity versus time should look like a square wave, because this linear rail, this object moving back and forth, it has a constant velocity, hits it into the rail, then it's moved forward. Okay, and it repeats that. So this should be a square wave. The bottom one, the one variance of 1, is the best representation of that. And then in range versus time, this should look like a triangular wave. You know, the rate of change of that from the velocity of the target on the rail would be constant. So it would be a sawtooth, if you will. And the bounds, the gray bars, is where it should fit. So that's where it should lie on this, and also here in terms of velocity. All right, now I'm jumping to some Doppler rail measurements that we conducted just before the pandemic hit last year. We were integrating cameras with the radar, and we went up out there to the range and set up this Doppler rail at 450 meters. I think here's some of the guys working it. This is me here. There's our rail with the sphere. Okay. Also, when we were out there, there's another test going on. They had this equipment. These are 5G router boxes out in a certain range. That's all they are. Kind of like birdhouses on a post. Turns out we saw every one of them. Okay. Here's a video of the rail moving back and forth. See it going? Yep. All right. All right. Here's some actual data from that outdoor test. What we're looking at here is range in terms of meters, and then time. So when I started the radar, I got all these different tracks coming up, and most of them stayed with me. Turns out these are those boxes. Okay. In the next slide, I'll show you. But what I wanted to focus on is the Doppler rail. So that's right here at 450 meters. I pulled this data into Excel, did some analysis. Now I've got a little easier package, which would be real nice in the future. But what I looked at here, I took a small distance zone, and I think I used a 0.3 meter range. So if any of the Doppler target tracks fell within, this finite region, I wanted to collect it, because this should be repeatable data. I'm doing the same thing over and over, and I would like to think that would be, shown in the results. Turns out there's quite a bit of variability. If you look at the min and max, let's look at the velocity. So its reported velocity is from -19 to -2. So clearly that -19 is in air. We've never, we're at, I don't know, 3.5 meters per second, I think is the number. But you get this variability. You also see sometimes a track will jump into something else. And I don't think this is really based, this data is not legitimate, okay? It's the tracking sphere, whatever, trihedral, did not do this. It stayed in this region here, but yet the tracker is telling us it went off like that. And that's when you get these wild errors, when it jumps and makes assessments. My conclusion there is we really need to have a different way of making this Kalman filter fit the dynamic of the data. Okay, we can't just use one number for everything because it doesn't fit. If you look at just the first point, so as it comes in and hits that distance, This is the data here, -8 to -2 velocity. RCS doesn't look that terrible here. Anyway, we'll keep going. Here's one more looking at the backside. Here our velocity swing is from 2 to 22. Again, get some erroneous results in there. And we got to be able to sort this out, right? We can't react on data if it's not valid. And so that's part of the ongoing work is how do we make this data more valid, right? I mentioned those boxes on posts. I got the GPS coordinates from the researcher and plugged them here in on this map. And this, exactly correlated to where I'm getting those range returns. If we were to dig in a little deeper and look at individual data, so this is the one that's up front that was in that picture. This plot here is azimuth, and we're going from, say, -4.5 to, I don't know, call it -2.5. So a 2-degree swing. This thing is not moving. This object is not moving. It must be just vibrating enough. It's a pretty small wavelength where it's, got a little vibration, and the radar's picking it up consistently. But it is giving a little bit of erroneous data on the azimuth. And elevation is even worse. Here we go from -1.5 up to, almost 2.5. The range is very good. This Doppler radar does measure range distance very, very well. And it measures radial velocity well, at the detection level. But then when you try to squash that data into a track and make assessments on that track data, that's when I think it goes a little bit awry. The velocity plot here also looks pretty good. Nothing glaring, right? Keep going. All right. So the next test we're talking about here was some ground data assessments in preparation for airborne test, where we have an algorithm called Icarus using the airborne radar data to help navigate it. So that was the end goal. This was the first ground test out there at MAPS, Virginia Tech, to begin looking at that. So the red traces are the Inspire drone. So I think what it did, I think it flew to here, then went across this way, and then came this way and did this, and then did one more time here and then back. The black circle is depicted here. Oh, the white, of course, is the radar track. All this stuff here is birds, most likely, right? But you do see the Inspire as it's being tracked. But you don't see it tracked right here, and you don't see it tracked right here. I think this is a good example where the path of the aircraft actually has 0 radial velocity from where the radar is. Now, so if you look at this arc right here, that would be the location of 0 radial velocity. Now, normally you would have the radar at the center, then you would have the right arc length. But even without doing that, because it would be, off the page and I couldn't quite get centered, I think this depiction is still valid, even though your arc length may be a little different. And here in this region here, if you were to expand that, if you were to expand that, you would see that this region here also would have 0 radial velocity. So the radar will not track something with 0 radial velocity. Okay. Right. The next slide is where we actually went to Virginia Tech and flew our own ship with the radar against both that Tempest as shown there, and then a Cessna. I wanted to, this work was highlighted in a NASA Raven final report. Andrew Chris was the first author, I was second. So you can, maybe pull that up if you want to learn more. But this group of folks at NASA, Lou Glab and his team, they do a lot of this type of work. And I wanted to mention this work on Isaac. This is a video of some work they did. If you want to jot that down and get it off my slides, it's worth looking at. A very nice little presentation of work using low power FLARM sensors for detecting void. All right. The next slide here shows actual flight data. We're going to see an image of the own ship, its path, which is the BFD, and then the Cessna. So let me just play it. I'll play it a couple times. The BFD is up here on the top. Here's coming in, and the Cessna's coming in here. Here's that radar track. It's quite a bit off from, where that vehicle is. I mean, in terms of GPS, that's quite a bit of separation, I think. So the BFD did make a maneuver and then started back on its return path. So these are birds and things. I'll show that one more time. Here's the BFD coming in. It sees the Cessna right about here, and then it starts making that maneuver. Okay. And then it resumes course and starts to see other things to track. This was a pretty challenging measurement because there was so much clutter, birds and also ground. We did a lot of work trying to mask out different regions of the range view that were giving us problems. All right. In terms of current work, I've been working with Chester Dolph recently, trying to look at this data, make sense of it, and then apply AI to help determine, quantify what's a bird, what's a legitimate, aircraft, what's ground clutter. And again, we're using cameras, also integrating camera vision with the radar to help give a better solution for this. And that work's going to be reported this August in an AIAA conference. Okay. Last month there was a test, and then actually last week there was another test. This is kind of what that test looked like. This here is the actual radar script, and what all this coding means is our field of view is the black line. Then we've got some zone masks here out to a certain range. We don't want to see the tree clutter, so we narrowed it down. The zero radial velocity points are here. There was one flight configuration that was this purple. I think we ended up not doing that because this region here and all this region here would essentially not be seen because it has zero radial velocity. But this is the certain range at NASA. All right. This is data track ID versus time. So I mentioned early on that this radar can only track 20 consecutive objects. Okay. And this here image is a pretty good depiction of that. If you count to 20 here, and then as soon as you get another one's dropped off. So it can only maintain 20. But here's those different objects that we saw throughout the thing. Some of these were actually buildings. If you look at the data closely, you'll see some numbers of say minus 50 dBSM, which seems imaginable, but you're looking at the side of a building. It's probably a garage roll-up door, and that thing's probably vibrating just a little bit, and it's a constant track for the radar. All right, conclusions and recommendations. So in order to do a target classification, we've got to do a better job with our range resolution. 3.5 or 3.25 meters might be good enough to, establish a Cessna versus a 747, but it certainly is too coarse to determine if this is a 500-pound drone or a 50-pound drone. So I'm under the, impression what we need to do is increase our bandwidth. If we can get 200 megahertz bandwidth, then we're looking at about, a 1 meter resolution, which is a lot better than 3.25. My other comment here, the spectrum allocation, if you've got interference from other drones, this is, other drones using similar radars in this 24 gig band, this navigation band, it's problematic and it's not going to be scalable. So we really need to be, cooperative in how regional spectrum is utilized for this surveillance navigation. Let's see. Effective operational surveillance volume is compromised by 20 track limit. Their spec, if they were to have to prove that out, some sort of measurement, I don't think they could do it. I think there's going to be more tracks that are occurring where you're going to have a really hard time demonstrating that you can measure a 0 dBSM target at 2,500 meters. My question would be, at what degradation of field of view? Because you're going to really be masking that a lot to ensure you've got data from that, one range cell at 2,500 meters. Anyway, I think there's my recommendation. I think we really need to use AI to filter these tracks out very quickly and eliminating them so you can still maintain this search volume and track efficiently and not worry about things that you shouldn't, like ground clutter or birds or things like that. I mentioned the Kalman filter variance settings. I think we need to look at dynamic filtering where you can, get a best fit of that behavior rather than using some static number. Now I'm going to go with some recommendations. I think the beam angle error that we see, and this particular company, they would tell you in elevation, they would expect 1.5 degrees beam error, and in azimuth, 1 degree. And that's, I think, directly related to the beam width of the AZ and L beams. And again, that's E and H plane, if that makes any better sense. I think you can improve the beam angle greatly if you had a second antenna, one that's, the passive scanning where you can collect data while the core radar is transmitting dwell time, if you will. You can scan your second receiver, put it at a null, and pinpoint exactly where that is. If you had 2 of these passive scanning receivers, I think it would allow you to generate an unfocused cross-range imagery, which could give you size information. So not only would you have a downrange, you could get a volume. Well, at least area. It wouldn't be volume per se, unless you did something else. Let's see. I also think that you could expand your operational field of view by using a passive scanning receiver. You would essentially be using the radiation from the transmit antenna in the regions, beyond plus or minus 60. The secondary receiver, you could point it and have your peak beam down there from say minus 60 to minus 75 and increase your field of view. It's not going to help you improve your range distancing, but for close in targets, it would give you a better estimate of position. I really think we need to explore multi-static radar systems to generate additional information. I would actually like to see information passed to the radar. In fact, you could use the radar to pass information, right? Couple things here. If you knew the pattern, the algorithm of the search grid that this radar is using, and you monitored it from afar, you could then determine, okay, based on what I'm seeing this radar do, I can make an assessment of how much congestion is in that airspace. Okay. Also, I think you could make an assessment of turbulence. If you have a transmission that's constant and just varying due to turbulence, where you're changing the phase of this transmission by oscillating back and forth, a little bit of movement, I think you could back out the flight environment, which I think is a pretty cool thing. There's a need to increase the signature of your vehicles. If you could get it up to about plus 10, that should give you enough margin of error, I think, in terms of being detected and being able to maneuver in time. This radar doesn't have a chance really of working well for a target at minus 32. The mathematics just aren't there. All right, regional assessment to enable more effective operational utilization is recommended. I think we can use our spectrum smarter, and embrace spread spectrum. That's a big push. Particularly for the radar bands, folks are wanting to use this band for other uses, and I think it could if we're smart about how to do it. All right, couple other conclusions. Data not needed by you does not mean it's not needed. I think if you've got a drone flying, say 400 feet off the ground that has a side lobe looking at the ground, you could easily determine if it's you know, what the road conditions are. Is there snow on the ground? Is it a flooded area? Is there a fire region, you know, where the tree lines have dramatically changed their signature? That's where the fire line is. Rain, I'm sure, is going to influence this thing. So using the side lobes to collect data, even though your main beam is not pointing there, I think is still a valid approach. I mentioned the airspace congestion and turbulence. And then my final thought here, radar cross-section signature by itself is less valuable than physically sizing an aircraft. These estimated RCS numbers coming from this radar are not very good. Maybe they're within 10 dB. That's how I would put it. But it really doesn't tell you much about the size of that vehicle. And I think if you could implement these additional antennas with the reference to the radar, then you can get some unfocused SAR and give you a better idea of the actual size of the vehicle. So with that, I am done. Happy to take questions.
Okay. Thank you very much. Okay, any question from cyberspace? Any question from cyberspace? Okay, well, why didn't I ask the first question then, George? You mentioned the challenges basically right at the end. So the sky is going to be denser. Everybody is keep pushing for high frequency. But where do you think the limit is going to be? I mean, because there is a scarcity of frequency, availability of the frequency as well. How do you resolve this problem? Because by 2030, NASA believe that there are going to be, you know, over 500 million hours of flight delivery, so on and so forth. Do you think we're going to be ready for that day?
I don't know. I think it's going to take investment. You know, NASA's approach, at least for this airborne radar, is to let industry take care of it. And I guess I'm kind of the first one raising my hand saying, hey, guys, we may not be there relying on industry. If this is what we're getting, we need to maybe step in and help augment. So that's kind of what I'm hoping comes out of this, you know, this effort.
I see.
In terms of let's talk spectrum allocation. So there's a lot of flexibility, honestly, in this waveform and how you use it. And if just one of the frequencies is interfered with, I think you can manage that. I think you can still get the data that you need. So I would take the approach, expect there to be some interference. So how do you mitigate that? You know, there are schemes that are out there to help you separate an interfering source from another. But I think you can also build enough robustness in the waveform and in the processing. So if you did have one bad data point or no data point at all at a particular frequency, you could still get a fair estimate of what's out there. Does that answer your question?
I think so, yes, thank you. And then let me ask another question. This is a naive question that I always have. All the information that you and many others are sharing is about ground and sky. What about underwater?
I'm not sure what you're asking. What about underwater? What do you mean?
Okay, you mentioned about remember the Jupiter?
Oh, yep.
Yeah, but then can you have a similar information for you know, about the ocean?
Oh, sure. The surface of the ocean, absolutely. Yeah. You would be able to characterize the, you know, height of the waves, that sort of stuff. Sea clutter, you know, which is related to the wind and the chop of the surf on the ocean. Yes. This won't work beyond the surface, or not much beyond the surface. I guess if you had a submarine sitting right below the surface, maybe you could detect that from the clutter of the reflection of the water. I don't know. But certainly the surface of the water would be characterized by this radar, yes.
I see. Okay, thank you. Okay, any other question?
Hello, George. I'm Rapi. I have a question about the Doppler radar's application in, light precipitation. Is it possible to detect lighting precipitation, for thundering using the Doppler radar?
I'm sorry, your volume was low enough where I couldn't quite hear you and I couldn't get to my adjustment. Could you increase the
Yes.
volume and repeat that, please?
Yes, I wanted to know that using the Doppler radar, we can accurately measure the speed of a wind and so on. But what will happen that if the speed is faster than light, then can we measure using Doppler radar?
I'm sorry to say this, but I still didn't quite catch your question. You're saying if we have a Doppler radar, can
Yes.
we measure?
Yes, speed more than light, then can we measure using Doppler radar?
Okay, his question is if is right is if it's
Speed of the object is higher than the light.
okay, okay,
Higher
yeah,
than the light. What do you mean by
Yeah.
light? Speed of light?
Yes, for
yes,
example, lightning, because it is a very few moments of milliseconds, and it is very fast. Then using the Doppler radar, can we measure such interterrestrial situation? That was my question.
Can you monitor lightning with this Doppler radar? I think that's what the question is. Right?
Yes.
I don't think so. I actually did a lot of lightning research earlier on in my career. That was a lot of fun blowing up composite panels. When lightning propagates, it's not that fast. It's very finite. It kind of jumps around. It makes an electrical threshold of the air. And then it can jump through that threshold, and then it does it again. So it's like discrete little jumps. If you look at the very high speed videos, if you've ever looked at that, you'll see that to be the case. The propagation is very discrete. No, I don't think there's any backscatter return that would be detectable. I say that I've never tried to measure radar with measure lightning with radar, but I think it would be a very difficult thing to do. I just don't think there's enough reflection from that to give you a response. That's my thought.
Okay, thank you for your answer.
Thank you.
okay. Is there any other question? We have time for one more question. Okay, if not,
So I would like to make one comment. Any of the electrical engineering students, I would encourage you to, look at this field. There's a need for folks doing RF type measurements. Been a very fun career. You get involved in a lot of different things. Your Europa satellites to, lightning. So a lot of room for research. And if you're ever interested, NASA Langley's looking for folks that have this kind of expertise. So I encourage you to apply once you graduate and come join us.
okay, yeah, in fact, my colleague, Professor Bin Yang, he's part of this group that is listening to you right now, and there were many other students that simultaneously, some of our students are in the other group listening to an interview with a candidate. But your talk was really interesting. Thank you so much, especially being very detailed, and appreciate it. And hopefully I'll see you sometimes in Hampton myself.
Very good.
All right. Thank you.
Thank you for having me. I enjoyed talking to your group. Thank you.
Okay, pleasure. Thank you so much.
Bye.
Everyone have a good weekend. Bye-bye now. Bye-bye.